Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to lecture 3 in week 5. Today we are going to talk about state-of-the-art thermoelectric materials and some of the factors that determine the optimum band gap and band structure of thermoelectrics. You saw in week 2 by Professor Lundström that the transport function or transport distribution function, or otherwise called differential conductivity, determines the electronic properties that can be used to calculate electrical conductivity as well as the Seebeck coefficient. The factors that enter this transport function are the Fermi-Dirac function, the group velocity, the scattering time, and you multiply all of them, it gives you a function of energy. The average energy of this distribution is the average energy of moving electrons. The difference with respect to the Fermi energy is the definition of the PbTe coefficient or the Seebeck coefficient. So the question is, based on this microscopic picture, how we determine what is a good thermoelectric material. So one way to do it is you put parameters for different material that you can deal with. As a part of the homework, you will work with a transport simulator in nanoHUB that takes into account realistic materials like lead telluride. You can input what are the different bands, what are the parameters, or you can assume even a simple constant relaxation time. This is a good way to get intuition. And then the program calculates what are the density of states and this transport distribution function at different dopings, and what are, for example, the calculated Seebeck and conductivity. By playing with this, you can start to get to understand some of the trade-off that there exist when you change some of the scattering parameters, the energy dependencies, how the electrical conductivity and the Seebeck coefficient change. So the question of how the figure of merit, which is the macroscopic property, Seebeck square electrical conductivity divided by thermoconductivity, is connected to microscopic properties of material, was first discussed by Chasmar and Stratton in 1959. He defined a material B parameter that I will kind of simplify it here, which is basically mobility of electrons times effective mass of electrons to the power 1.5 divided by the lattice thermal conductivity. That's what determines really how good is a material for good ZT. This mobility of electrons is directly proportional to tau, scattering time, mean free time between scatterings, divided by electron effective mass. So that's what is the key part of the figure of merit. What determines the lattice thermal conductivity in the limit of high temperatures, that's only in that case, phonon-phonon scatterings, Zumklapp scatterings dominate thermal conduction, and this is an expression called K's relation that is very important, because this expression tells you to get a material with low lattice thermal conductivity, you need a material with low melting temperature, with low density or large interatomic distance. Then you have A, mean atomic weight to be need to be large, and finally gamma, the Gruneisen constant, need to be large. Gruneisen constant describes phonon-phonon interactions. The larger it is, the more scatterings you have, and that's how you can reduce the lattice thermal conductivity at high temperatures. If you just look at tables of different semiconductors and what are their mobility times effective mass squared divided by thermoconductivity, just measured value, you see that it can change by orders of magnitude, and without any specific approximation, you can see already that bismuth telluride, silicon, germanium are material with good properties. The next level are a lot of 3.5s, but an order of magnitude lower here. The question of material with good mobility is because electrons move well, and low thermal conductivity because heat doesn't go well. Effective mass really comes because of the band structure, because of the asymmetry of the distribution function with respect to the Fermi. If somehow we are able to somehow engineer it so that the effective mass doesn't come in. If you only consider mobility divided by thermoconductivity, the picture changes. Actually, a lot of the 2,6 and 3,5s, like indium antimonide, InGas, as well as mercury cadmium telluride and so on, are already much better than some of the existing thermoelectric material. Often it is said that we need a good electroconductivity, bad thermoconductivity for thermoelectrics. Based on this criteria, this is not the dominant factor. The effective mass plays a big role. One has to pay attention. There is a very interesting article, a set of 2 articles about what is an optimum band gap for a thermoelectric. Knowing what we know about the microscopic picture, how those parameters of effective mass and scattering time and so on change with band gap of the material. Again, the original study goes back to Stratton, Chasmer and Stratton, but Mahon in '89 for an indirect band gap material calculated this type of ZT max versus E gap divided by KT. These are 2 parameters given for different scattering exponents. This is how energy dependent scattering, what is the power factor as for the case of phonon scattering or impurity scattering, and the dash versus solid is different B parameter. That's the better material, but you already see that the optimum thermoelectric have a band gap which is bigger than 6 to 10 times KT. At higher band gap, this stays constant. In this case, doesn't go down. The reason we use lower band gap is typically higher band gap means stronger bonds, higher lattice thermoconductivity. In 1994, Sofa and Mahon generalized the analysis for the indirect band gap material for direct band gap material. What is the difference in the direct band gap material is that in that case, effective mass and band gap are directly related through Keynes matrix element. So you can actually consider also the fact that the scattering time themselves are effective mass dependent. You get a slightly different picture, but the curves at the end doesn't change as much. This is ZT versus E gap divided by KT. Again, you see an optimum 6 to 10 times KT, so that's kind of the rule of thumb people believe today. But you see, for example, in the case of ionized impurity and non-parabolic bands, this keep going. That means larger and larger band gap are better if other parameters stays the same, which is the lattice thermoconductivity. So this gives you an idea about the rules of thumb, how thermoelectric materials are optimized at each temperature range. There is a recent study by Professor Lundström that it actually follows directly from the lectures you had in week 2 on the Landauer formalism. And this was also one of the articles for week 2 that was referenced, where they approach the problem of optimum band gap differently. They look at an ideal model, but they consider this Landauer approach, and they calculate what is the optimum bandwidth, width of the band, contributing to conduction, to get the highest ZT, highest thermoelectric property, if the lattice thermoconductivity is 0, or it's some finite value, non-zero, but small, like let's say 0.5 watt per meter Kelvin. Basically, their prediction is, of course, when you get to the delta function, you get a type of ZT kind of diverging, very small bandwidth, KT or lower, large ZTs. But you see already the power factor, S square sigma, Seebeck coefficient square sigma, has a maximum at finite width. When you go to a smaller width, because conductivity becomes smaller, your power factor is smaller. So really the main reason ZT is diverging is the Lorenz number, the electronic contribution to the thermoconductivity that goes down, and that's a key parameter. When you add a slightly finite thermoconductivity, that is really the case all the time, then the optimum bandwidth is not a delta function, and it's a couple of KTs, because at this level the heat leakage through phonons will dominate. What is interesting is that this article talks about optimum bandwidth, take an approach which is Landauer, and the previous articles by Mahon discuss, look at the problem differently. They calculate the optimum band gap. It's actually a very good exercise to see how from the formalism in this paper one can relook at what Mahon did earlier on the optimum band gap. It's a good way to get intuition about microscopic. These are some of the conclusions of this article that I put it here just for you to look at it. If you're interested, you should look at the article. You saw in the previous one, when you do idealized case, this Lorenz factor, which is the ratio of electronic thermoconductivity to electrical conductivity. This is the Widman-Franz law from 1850s or so. Often people give a constant expression for that, for the Lorenz. But this is really depends on the band structure. You saw in the ideal case it can be as small as 0. Here is a paper from 2007, Zishibian and others, for a realistic thin barrier superlattice in gas, indium, gallium, aluminum arsenic, how the Seebeck coefficient and Lorenz number change as a function of doping. And we already discussed in lectures in week 4 about non-monotonic behavior of the Seebeck, but here the yellow line show you the Lorenz number, and you can see the Lorenz number with realistic material parameters can change easily by 50% or sometimes a factor larger. Now let's look at some of the classic thermoelectric materials. That's what used today in a lot of commercial application. Z times T as a function of temperature for different material has a peak, and this peak actually kind of rule of thumb still applies. Larger bandgap material have peaks at higher temperatures. Bismuth telluride, first discovered 1955, Joffe and Goldsmith. Lead telluride, 1960s. Silicon germanium, 64. Rossi tags, I will describe it, 1961. So this is the date they were developed. Here you can see some general observations from Siddharth Uher's lecture at APS in 2006. Basically, for the standard bismuth telluride, lead telluride is highly anisotropic in a single crystalline form. In plane Z is better than the out of plane Z by almost a factor of 2. Tellurium-thorium van der Waals bonds between layers. So this is one of the reasons this type of materials have become exciting when people are studying topological insulator 2D materials. And this was really the original idea of Joffe to use solid solution to improve ZT. Still used in 90-some% of applications of thermoelectrics today because of very good performance. Lead telluride is rock salt, has a high dielectric constant. At high temperatures, there are issues with the loss of tellurium. A variant of lead telluride was discovered by Rossi et al. In 1961. It's called TAGS, which stands for tellurium, silver, germanium, and antimonite. The ZT of the P-type at this temperature range could be as high as 1.5, but there are some significant stability issues. That's the reason it is not as much widely used. Silicon germanium is another very surprising case because of the very high melting temperature and a high Debye temperature. It is expected to have a high lattice thermoconductivity, so it's not expected to be a good thermoelectric material. But the exceptional low lattice thermoconductivity open alloying, when you add a little germanium to silicon, was discovered by, measured by Abels et al. In 1962, and the standard Clemens theory can explain this, but this is a case of a lower effective mass material because of this and usually lowering of the thermoconductivity by alloying, it becomes still very highly used. Silicon germanium material has been used in the space applications, as you saw in week 3 for some of the applications. Let me finish today's lecture with describing of some of the complex chalcogenides. When you mix bismuth telluride, lead telluride with some alkali metals, you can get very good thermoelectric properties. An example of them, an early example from mercuric azides group is cesium bismuth tellurium, bismuth 4 tellurium 6, which has a ZT of 0.8 at 225 Kelvin. So this is one of the few good bulk materials at low temperatures. Addition of cesium really changes the structures of these, and the way forms are, the bonds are formed. So it's a very rich chemistry. Another material system based on complex chalcogenides that was pioneered by mercuric azides group is called LAST. Silver antimonide, silver lead antimonide tellurium with 18 lead is called LAST 18. Is a cubic compound. There are some phase segregation, is an N-type material, and one of the early success, ZT of 1.6 at 700 Kelvin. Basically, there are nano-size regions that are lead poor, and their endoepitaxially surrounded in the matrix. And as you remember in our first lecture in the week 5, second lecture in week 5, we discussed that this embedded nanoparticles in a couple of nanometer size are very efficient to lower thermoconductivity, and that was the key to success of this material. And this has actually been the basis of the best record ZTs up to date. This is for bulk materials. In September 2012, the same mercuric azides group demonstrated a ZT of 2.2, and the idea is quite interesting. First, you use the best type solid solution that is available, sodium doped lead telluride. These have a ZT of 1.1. When you add strontium telluride to it, it forms nano embedded nanoparticles. ZT is 1.7, and the size of these nanoparticles is 2 to 4 nanometer, a few tens of nanometer, but this is really nanoscale. Here is the bulk going from to the solid solution with strontium telluride, and you can see significant improvement in ZT everywhere, especially at high temperatures. But then an interesting thing happens when you do spark plasma sintering. You form domains, and these domains now range in size from 0.4 to a couple of microns. These are much bigger, and you can see these domains now are the reason of ZT reaching 2.2, but what is interesting is ZT up to about 700K is the same. This domain only help at high temperatures. As far as I know, this has not been theoretically demonstrated what are the key factors dominating thermal transport and how this domain play. The theory we describe for erbium arsenide and so on explain this behavior with nanoparticles, but not the other behavior. This is a good point to actually compare this data with the state-of-the-art transport solver. This is something that you can explore as a part of your homework. Boltzmann Transport for lead telluride need to consider 3 bands, L valley, gamma valley, and sigma. These are the band gaps at room temperature. And this is the separation with the heavy band. This is anisotropic and non-parabolic, so the effective masses are given in different directions. All of this can be included in the model. From a scattering point of view, acoustic phonon, polar optical phonon, and impurity scattering is included. And then using the standard transport function differential conductivity and the parameters given by these papers by Chris Vinay's and Ravich et al. Can be used to model lead telluride. How these results compare with experimental data. Here are the experimental data of this record ZT 2.2 from Chalcogenides. Conductivity versus temperature, Sept versus temperature. The trend is not unusual. Conductivity goes down with temperature because of additional scattering. Similarly, Sept goes up. They measured a carrier concentration of 9 × 10⁻¹9 at a certain temperature, not on the wide range. What you can see is that the lead telluride with just kind of a bulk material is here with 2% sodium doping. Then you put 2% or 4% of solid solution of strontium telluride. You see similar electrical behavior, slightly reduced here the electrical conductivity, but when you do a spark plasma sintering, then the numbers go down by almost a factor of 2. Seebeck is almost unchanged within this range. Here are the calculation by Jehan Bach using this Boltzmann solver that you can use in your homework. So at this doping, if you put pure lead telluride, this is the Seebeck you get, and this is the conductivity you get. If you compare it with experiment, Seebeck is exactly matches. Conductivity is lower by a factor of 3 or so, or higher. So definitely mobility is suppressed by boundaries, and you can see it here. But what is interesting is if you put the pure lead parameters at high temperatures, the doping at high temperature was not measured in this paper, so we had to estimate. We put 1.5 10 to the 20th, increased by almost a factor of 50% comparing to room temperature. Why? Because of this additional, the nanocomposite could become additional donors, or you could have additional ionization of the dopants. Then you can, with this doping, you can explain the Seebeck, but you see the conductivity is not that far from pure bulk silicon. So what it means is that at higher temperatures, because the mobility is inherently smaller, you feel less the effect of nanocomposite and the grains and so on, and that's one of the key requirements to get high ZT. Here are the measured total thermoconductivity, inferred lattice thermoconductivity for this material. They have a total thermoconductivity of their best material about 1 watt per meter Kelvin at high temperatures, about half of that coming from lattice. Here are the calculated electronic thermoconductivity using the same Boltzmann solver. So at the same doping, we can get similar type of electronic thermoconductivity that they have. You can see this behavior. If you could increase the doping, this goes up significantly. That's the Wiedemann-Franz law. And at low doping here, you see there's another going up. I think this is a range where bipolar conduction starts happening, and that's contributing to electronic thermoconductivity. Let me summarize week 3. The optimal band structure for thermoelectrics, we discuss about it. We discuss what are the requirements to get the lower Lorenz number. Then we reviewed what are the classical thermoelectric materials, bismuth telluride, lead telluride, tags, and silicon germanium. Then we spent quite a bit of time on complex Chalcogenides, examples at low temperature, but detailed analysis of a spark plasma sintered, latest lead telluride base material with the highest ZT, the fact that the Boltzmann modeling can explain the result, and different length scale from nanometer to micron are essential to model the phonon, to scatter the phonon and lower the thermoconductivity. Next lecture, what we will do is we will look at some of the recent advances in thermoelectric bulk materials and give you an overview of that. Look forward to seeing lecture 4.